In this video we will see one step subgroup test, one single step. One step subgroup test. Let G be a group. In group we already have a group first. G be a group. H be a non-empty subset of G. We are not writing G star. Star is in the background. We have one operation. If the single step is a B inverse belongs to the subset H for any two elements of the subset H, then we have H is a subgroup of group G. So the step is for any two elements of the subset H, A B inverse, it is the inverse of B. A B inverse also belongs to the subset H. And A B inverse are operated under the operation of group G. We are using multiplicative notation. Let us prove this. In proving what we will show, we have to show that H is a subgroup of group G. So H is a group. We have to show that H is a group under the operation of group G. So H must satisfy all four group axioms. And the theorem says, if H has only this property, H is a non-empty set, and H has only this property for any two elements, then H has all group 4 axioms. Let's first see the inherited property. We'll see the easiest part first. First one is associativity. It is the inherited property from the group G, and we can only write as the operation is associative in G. It is associative because associativity is a rule and it satisfies for a bigger set, so it will must satisfy for the smaller set H. So associativity holds. And next we will show the existence of identity. And there is no order. You can show any axiom first and any axiom second. There is no order that we will first show closure, then associativity, then identity, then inverse. Now we will show identity. It is given that H is non-empty. We are using this term. H must be non-empty. Since H is non-empty, we have an element small a in the subset H. And the property of H says, for any two elements, you have A and B inverse belongs to the subset H. And this A, B can be same, both elements can be same and it can be different. And there is no condition on A, B. A, B are just two elements of H. B can be A also. they both can be same. By the property of, by given condition, we have A and its inverse when operated are also in the subset H, and this is nothing but the identity. We are using multiplicative notation, and E is the identity. In multiplicative notation we can use E or 1, so we have identity. Next we will show the inverse. We'll show that take any element in the subset H, its inverse also belongs to the subset H. And we will start from any arbitrary element A in the subset H. As identity is in the subset H, since identity is in the subset H, we have one element identity and we are taking another element A. It can be identity, it can be any other element. We have, I can take this one first, and its inverse also belong to the subset H, and which is nothing but A inverse because it is identity. So A inverse is in our set for any arbitrary element A of our set H. So therefore, for any element of this set, we have its inverse also in that set. Next, we will show closure. I have kept closure last because we will use this to. In closure, we have to take any two arbitrary elements and we have to show that their product also belongs to their subset. Take two elements from the subset H and we have to show, let us write what we have to show. We have to show, we will show that AB is also in the subset H. See, since B belongs to the subset H, its inverse also belongs to the subset H. By the above, we have already for any element in the subset H, its inverse belongs to the subset. So if B is in the subset, then its inverse also belongs to the subset. And we have one element, I can use this element and this one, and with the property of the subset, I am taking the second element as B inverse. So I will take this one inverse. This is one element of H. A, C, suppose this one is C. A, C inverse is in the H. If A, C are in H, belongs to H by the property of H. We have this property, H has this property, and we are showing that H satisfies all four group axioms, and that implies AB, because B inverse of inverse is same element, and we are starting from the starting point is, suppose we have the property, we have the given property. Suppose H has the given property. Suppose H has the given property, and we are starting from here. We have the property given, then we are showing that H will satisfy all four group axioms. Pause the video to note. Let us see example. Let us start from the simple example. first example is, suppose our group is the set of integers under the operation addition, and I am taking a subset. Suppose it contains all even numbers. It is a set of even numbers, set of even numbers, or in rule form we can write 2m for m an integer. For any integer m, 2m is in the set E, and that is the property of even numbers. If m is 0, we have 0, 2, 3, not 3, 2, 4, 6, 8, and in negative -2, -4, -8, and so on. And this is the set of even numbers. And we have to show this this set is a subgroup of G. We have to show is a subgroup of group G. First of all, we will show that E is non-empty. Then we will apply one-step subgroup test. By one-step subgroup test, first we will show that E is non-empty. E is non-empty. E is non-empty. We have to show some element belongs to the set E. We can take 0, or let us take 100. 100 belongs to E, as it is even. That implies E is non-empty. And why 100 belongs to? As 100 is 2 times 50, and 50 is an integer. This is as. So we have our non-empty set E. Then we will apply one-step subgroup test. Let us take 2 elements of the set E. Then we will show this B inverse also belongs to that subset. And we are taking now, let we have A and B in the set E. So by the property of set E, what we have, that implies A equals to 2 times some m, and B equals to 2 times some n for some mn belongs to the set of integers. This is the property of set E. If A and B are in the set E, it should be of some product of 2 times some integer. So A is of 2 times m, and B is equals to 2 times n for some mn belongs to the set of integers. We are using additive notation. So this one-step subgroup test in additive notation will be, in additive notation we will have, in additive notation says for any AB in the set H, difference, this is quotient and this is difference, and we have seen this in the notation video. So now we will take A minus B, because our operation is in additive notation. A minus B equals to 2m. We have to show this one also belongs to the set of integers, a set of even numbers, is equals to 2 times, I can take common because we are in the integers. 2 is an integer, this is the integer product, this is difference. I can take 2 common, and I can write this belongs to the set of integers, since m and n belongs to the set of integers, I have m minus n belongs to the set of integers. So I have taken two elements from the set. We have E and its difference a minus b is also in that set. So by the one step subgroup test, we have by one step subgroup test we have E a subgroup of group G. Pause the video to note. Second example, we have G an abelian group and H is a subset of G and it contains all those elements of G such that when they are operated with itself you get identity, and we have to show H is a subgroup of G. We have to show H is a subgroup of, we have to show this one. We will use one step subgroup test, and one step subgroup test says H should be non-empty first, then we will apply this one. H is non-empty, H is non-empty. We have to show this one first. See, E, here E is the identity, E is the identity of G. Identity belongs to the set G and its square is E. So identity is one element. If I will operate with itself, identity with identity, then I will get identity. That implies E belongs to the set H. We have H non-empty. Next we will use the subgroup test. We will take any two elements for any AB in the subset H. We have to show that AB inverse is also in the subset H. Let us write that. We have to show AB inverse also belongs to the subset H, and to remain in the subset H, any element should operate with itself to give identity, which is AB inverse square must be identity. We have to show this one. Let us start from here. Now, AB inverse square is nothing but AB inverse with AB inverse. By associativity, I can write this one as parentheses are redundant. I can apply parentheses anywhere. I can change the parentheses. By associativity, this is equals to this one. This is not that implies. By associativity, and by commutativity, I can write this one as, let me write this first. This is by commutativity. And by associativity, I can write this one as this. This is by associativity. And this is A square A and B are in the subset H. Therefore, A square is identity, as A belongs to H, H square is identity. Pause the video to note. Let me erase first part, non-empty section. Oh. And this is equals to B inverse square, and we have to show that this one is identity. We have to show this whole thing is identity, and this whole thing is reduced to B inverse square, and we have to show this one is identity. We have what? We have B square equals to E. By the property of H, as B is in the set H, and if I will apply B inverse square to the left, right side we also have B inverse square, and which is, this is what? This is B inverse B, and this is B inverse square, and this is what? I can put parenthesis here by associativity, and this is B inverse E B, which is, and we have B inverse B, which is identity. So B inverse square is identity, hence I can write B inverse square is identity. That implies AB inverse square is identity. That implies AB inverse belongs to the subset H, and hence H is a subgroup by the one-step subgroup test. Thank you.